Good day, everyone. Today, we will discuss a distillation column problem with a given Murphree efficiency. Here's our problem. We have a binary mixture of benzene and toluene. Each component in the feed is 50%. It is a two-phase mixture with 50% vapor coming in at 400 kilomoles per hour. The reflux is 3 and the minimum reflux is 2. The compositions in the distillate and bottoms are 0.85 and 0.1 mole fractions respectively. This mole fraction refers to the more volatile component, which is the benzene. The Murphree efficiency based on vapor is 80%. The question here is how many stages are there? So for us to have a better understanding on this problem, we have here a diagram. So this is our feed on the left side in 400 kilomoles per hour, 50% benzene and 50% toluene. This is the midsection of our column. The upper part of this column, this is called the rectifying section. It has a condenser here and vapor is fed into here, and then the streams is divided into two, the L and the D, which are the reflux, liquid reflux back in our distillation column and the distillate. Below here in the midsection, this is called the stripping section. We have a reboiler here. Liquid is fed in the reboiler, and there are two streams coming out from the reboiler, the bottoms and the vapor also that is going back to our distillation column. In our problem, it is stated that we have a total condenser. Total condenser means that every vapor that is fed into this total condenser, it turns to be completely a liquid. So 100% of the vapor that is fed becomes a liquid. That's what it means in the total condenser. And this partial reboiler, so from the word partial, so all liquid that is fed in this reboiler, only a percent of this liquid is vaporized. So in other words, not all the liquid that is fed is vaporized. We'll go back to our diagram. So we will analyze first the top part, which is the rectifying section. So this is the equation. V is equal to L plus D. So that's the vapor here, vapor, and the L plus D. So as we expect, V is equal to L plus D. The mole fraction of the benzene in the vapor is designated as Y. In liquid, it is X, and XD in the distillate. Then the equation becomes Y is equal to L over V times X plus D over V times XD. And we know that V is equal to L plus T, so it becomes Y is equal to L times X over L plus D plus D times XD over L plus D. Then rearranging, so we arrange this equation, and knowing that R is equal to L over D, the equation then becomes Y is equal to R times X over R plus 1 plus XD over R plus 1. And we know that R is equal to 3, as stated in our problem. So the reflux is 3. The equation finally is Y is equal to 0.75x plus 0.25xd. This is the slope. The slope is 0.75 and the y-intercept is 0.25xd. xd here, as given in our problem, it is 0.85, the mole fraction of benzene in our distillate. So 0.25 times xd, which is 0.85, our y-intercept is 0.2125. So that's our y-intercept. So we will plot this equation in our Excel. So remember, y is equal to 0.75x plus 0.2125. So we will start at the point of 0.85 and 0.85. So this is that point. And our y-intercept is 0.2125. So this is here. And we'll connect these 2 points. So that's our operating line for our rectifying section. So this red line is the operating line of the rectifying section. And then we will go to our feed line. So the equation of our feed line is equal to y equals q over q minus 1 times x minus xf over q minus 1. This xf is the mole fraction of benzene in our feed. Q is equal to L bar minus L over F. This is the L bar. This is the L bar, this is the L, this is the F. Now this L bar, this is equal to L plus the liquid component, part of our feed. So the liquid part of our feed is 0.5 F. So the question is, it becomes 0.5. It is stated in our problem that the feed is 50% vapor, and it's also said here that the mixture is two-phase. So in other words, it is 50% vapor and it is 50% liquid. Q is equal to L bar minus L over F. And we define that L bar is equal to L plus our liquid in the feed, which is 0.5 F minus our Q is L bar minus L. So L bar is L plus 0.5 F, and then minus L divide all by F. So our Q is equal to 0.5 F over F, which is 0.5. So Q now is 0.5, and plugging it in our equation, the final equation is y is equal to negative x plus 1. So remember this equation, the feed line equation is y is equal to negative x plus 1. So we go to our Excel, we'll start in the point of 0.5 and 0.5. That point is here, and the y-intercept in our equation is positive 1. Just that point, and then we'll connect these 2 points. So that's our feed line. The point of intersection of the operating line of the rectifying section and the feed line is this point here. So we'll have a point here in the distillate, 0.1 and 0.1. This point here, we'll connect this on a point from this point of intersection to the point of distillate, 0.1 and 0.1. This is the point. So that's the operating line of our stripping section. From this point of intersection, the point of the bottom 0.1 and 0.1. So this is what happens to our equation. So we solved here the temperature, the P1 sat, P2 sat, and alpha. We find the average alpha to be 2.44698. It was rounded off. So this is our alpha. Our XD is 85%, XF is 50%, and in the bottoms, the mole fraction is 0.10 or 10%. This is our graph of the problem. It's the graph of the distillation column. The question here back in our problem. The question is stages. How many stages are there? If you ask in the Murphree efficiency, it was said that it is based on vapor. the Murphree efficiency is based on vapor. So to start, we write if the process is ideal, we mean 100% efficiency. This point from 0.85 to 0.85, it will uh, it will reach until the equilibrium line. Write it here until equilibrium line. If the process is ideal, 100% efficiency, but the efficiency is 80% as given in the problem. So 80% of this line, so maybe it's here, and then we will write this is the 80% something in this line, and we will have a dash line up to on the bottoms. So that's the actual process, 80% efficiency, and then we will connect the points. We will make hub sum for the stages. So here up to this line, this dash line, this is called the pseudo equilibrium. So we'll make some lines here up to this pseudo equilibrium only, because this is our actual process. This equilibrium line is just a theoretical. And now we will count this line starting from here. We will not include the in some problems in this point, this is in the condenser, but it is stated in our problem that we have a total condenser. So total condenser, we will not include this in the counting of the stages. I mean, we'll start directly here at 1. We'll exclude the partial condenser, so 1 is 1 stage. Here, number 1. This is number 1. This is number 2. Number 3. Number 4. Number 5. Number 6. These are the stages. And in the last, it is stated in the problem that we have a partial reboiler. So partial, it is included in our counting. This is partial reboiler. In the question, as we go back, the main question is how many stages are there? So this answer our question, 6 plus 1 included in our partial reboiler. So the final stages, the stages that we needed, is 7. This was our line for the operating line, and our feed line is here. So I have to correct that. This point of intersection this point of intersection here in between, this point of intersection, we will connect that to the point of the mole fraction of benzene in the bottom. Here 0.1 and 0.1. This line is the operating line of the stripping section. So the intersection of the feed line and the operating line of the rectifying line connected to the point of mole fraction of benzene in the bottom, 0.1 and 0.1. Here below, it is the point in the bottom, not in the distillate. This is 0.1 in the bottom, the distillate is 0.85. I will have just to clarify that, because as I said a while ago that the point here in the lower part, this was distillate, so I have to correct that. This is the point for the bottom.